Alright, so this is part 2 of our stoichiometry series. In the first one we took a look at just kind of reviewing the stoichiometry process and looking at how we apply those concepts of stoichiometry to cases where we've got solutions using the molarity equation, sometimes instead of the molar mass equation. So what we're going to do in this particular video is we're going to do two applications of stoichiometry. Number one, we're going to take a look at applying stoichiometry to neutralization reactions or acid-base reactions, and then we're also going to take a look at how we apply these to limiting reactants problems. So again, limiting reactants is something that you've seen before. It just kind of applying it here. Neutralization is really just a special case of the stoichiometry that we've already seen. So, just as a review, what's a neutralization reaction? It's an acid and a base. Remember, acids and bases react together in a double displacement reaction, and the two products that you always get are a salt, which is some sort of ionic compound, and water. So if you take a look, I've got a sample equation on here, the reaction between H2SO4, which is sulfuric acid, and sodium hydroxide, NaOH, to produce water, HOH, and Na2SO4, sodium sulfate. So again, when you have those two things together, you always get a salt and water double displacement reaction. So if we were to do this exactly correctly, if the amount of hydrogen from the acid is exactly equal to the amount of hydroxide released from the base, then the resulting solution should be neutral. And that's the definition of a neutralization reaction, when you have the exact right quantity of an acid, exact right quantity of a base, so that when you mix these together, all you get is water. There's no hydrogens left over, no hydroxides left over. So how do we apply this to stoichiometry? There we go. In terms of this, typically what they're going to do is have you calculate how much of an acid is required to neutralize a particular quantity of base, or sometimes vice versa, how much of a base is required to neutralize an acid. So here's an example problem. What volume of a 0.1 molar sodium hydroxide solution would be needed to neutralize 25 milliliters of a 0.425 molar sulfuric acid solution? Now, a couple things about this. Number one, this is not a dilution problem. Again, you have two different chemicals present. This is not dilution. You cannot use M1V1 equals M2V2. This is a stoichiometry problem because you have two different chemicals present. So you have to write your balanced chemical equation. We've already got it because we used it on the first slide. But again, here's the strategy that I use. Typically, I will write the things directly below the chemical that I know. So I know that I've got a 0.425 molar sulfuric acid solution. I know I've got 25 milliliters of it, so I write it directly below that chemical. And I know I'm trying to figure out how much of the sodium hydroxide I need. So again, it's 0.1 molar. I know that from the problem. And I put, question mark for the number of milliliters. So again, we're going to use the molarity equation. We seem to use that all the time. And we're going to use the mole-to-mole part of our stoichiometry problem. So same kind of problem-solving strategies that we've used in the last video. So let's take a look at what this is. So starting off, number one, we're going to convert the number of moles, or kind of figure out how many moles of sulfuric acid that we have, because that's going to tell us how many moles of hydrogen we actually produce on there. So we have 0.01625 moles. If you take a look at how this works out, again, you're just rearranging the molar mass equation, sorry, the molarity equation, my bad. So multiply 0.425 times 0.025 liters. Yes, you must convert this from milliliters to liters. Move your decimal place over by 3. And we get our response here. We have 0.010625 moles of sulfuric acid that are present in that much of our solution. So then the next step, in stoichiometry, we convert from moles of one thing to moles of another thing. So in 3 sig figs, which is still too many. Why did I use 3 sig figs? I should have left that as 0.100. So let's just assume 3 sig figs. Anyway, so 0.106 moles of that. Here is our mole-to-mole ratio. Again, there is a 1 here and a 2 here, and that's where these two values come from. It's our mole-to-mole step, the stoichiometry step. So if we've got that much sulfuric acid, we need to have that much sodium hydroxide in order for them to balance out exactly correctly. And then the last step is we're going to convert from moles of sodium hydroxide back to, using our molarity equation, back to milliliters or liters of sodium hydroxide. So there's our rearrangement. Again, this is the one that I see students mess this algebra up all the time. Please be extremely careful when you're solving this particular problem. All right, so limiting reactants. Second version of our types of things that we have to do, other than neutralization reactions, is limiting reactants problems. And limiting reactants problems are just like the stoichiometry ones that we've done before, but you're going to have information about two different solutions this time as opposed to two different reactions. So now you're going to know, and again, how do you identify these? You're given quantities of two different, usually reactants, but they're both going to be given to you probably in molarity. So you're going to do your two stoich problems like we've done in the past, and then you choose the lesser of the two, the one that's the limited of the two reactants. So again, what's our problem solving strategy? Number one, As always, make sure you write your balanced equation, check your formulas. Number 2, you're going to use the molarity equation to figure out how many moles of each reactant that you have, 2 separate molarity equations. Then you're going to do your Stoich step, 2 little mini wonder fractions for both of your reactions, one for A and one for B or whatever it is. And then you're going to calculate all the way to the number of moles of whatever your product is. Then, when you've got those 2 answers, pick the least value. Whichever your least number is, that's your limited one, and then use that number of moles to calculate your final solution concentration that you need to get, or your final number of grams, or whatever it is that you need. So let's take a look at a sample problem here. So here's an example. Calculate the mass of the blood red silver chromate precipitate that forms when 50 milliliters of 0.25 molar silver nitrate is mixed with 30 milliliters of 0.25 molar potassium chromate solution. So number 1. Write your balanced equation. And again, this is probably where you need to get out your periodic table, your calculator, perhaps your little table that's got all the little polyatomic ions on it, whatever. But anyway, here it is for you. So silver nitrate is one of our reactants, and so here it is right here, AgNO3. Potassium chromate is our second reactant, and there it is, K2CrO4. Chromate's a 2-, so it's K2. And we get 2 different products. One of our products we know is silver chromate, because it says so open here in the problem. So here it is, silver chromate. Again, chromate, CrO4 is a 2-, so there's 2 silvers in that formula. And then our other product, because it's double displacement, has to be the leftover ions, which is potassium and nitrate. Finally, I went through and balanced it all. So it's 2 silver nitrates, 1 potassium chromate yields 1 silver chromate, and 2 potassium nitrates. So again, the strategy that I always use is I write directly below the equation the things that I've got. So from the problem, I know that I've got 50 milliliters of 0.25 molar solution, and again it's right here, 50 milliliters of 0.25 molar solution. I also know that I have 30 milliliters of this 0.25 molar potassium chromate solution, so there's those. And then it's asking me what's the mass of the silver chromate precipitate, so there it is right there. I'm trying to figure out how much of that I need. So you can tell in this particular problem I'm not going to be solving using the molarity equation as the last step. I'm going to be using molar mass as the last step because it asks for grams. So what do we do next? We've got our balanced equation. Next step is use the molarity equation to try to figure out how many moles of each reactant we have. So here we go. Here's our part 1 and here's our part 2. So when I take a look at the silver nitrate problem, I've got 0.25 molar, 0.050 liters. Again, you must convert from milliliters to liters. Move your decimal place over by 3. And when you solve it, I know I have 0.125 moles of silver nitrate. Do the same thing for the potassium chromate, 0.25 moles, 0.25 molar, sorry, and 0.030 liters, convert from milliliters, and I know I have 0.0075 moles of that particular chemical. So again, just applying the molarity equation to each reactant, 2 separate steps. So it's kind of part A and then part B. Now, moving on, we do the stoichiometry part. So here's the stoichiometry steps. Our 2 little wonder fractions. Here's the wonder fraction that goes along with silver nitrate. This is where we use the balanced chemical equation. We know that silver nitrate is in a 2-to-1 ratio because those are our coefficients from our balanced chemical equation. We've got a 2 and a 1 there. And we end up with 0.00625 moles of silver silver chromate that's produced. Our second little wonder fraction, we're going from potassium chromate to silver chromate, and these are in a 1-to-1 equation, 1-to-1 ratio, because again our balanced equation says that they're in a 1-to-1 ratio. So there we have it. So we end up with 0.0075. Again, the next step is to figure out which is the 2 is the least of the 2. So that's why I have the 0.00625 moles is the one that's circled. Because of their 2 choices, this must be our limited product. Silver nitrate must have been our limited reactant. So this is the one that we're going to move forward with because it's our lesser of our 2 values. All right, last step, we have to kind of go to whatever our answer is. In this case, our answer is looking for grams. Remember, it's asking us for mass. It could have asked us for a solution concentration or something else, but because this is a precipitate, it's going to ask us for mass. So we took our answer, again, our least of the 2 answers from the previous one, and then we use our wonder fraction to do the basic molar mass equation. This number right here is the molar mass of silver chromate. It's 2 silvers plus a chromium plus 4 oxygens, so that's where that 331 comes from, the molar mass of silver chromate. So there you go. There's our calculated value, and our final answer in 3 sig figs is 2.07 grams of silver chromate would be produced from this. So again, it's just an application of our stoichiometry problems that we've done before. You just have to do kind of the 2 of them side by side and pick the lesser of the 2 values. So there you go. Our main ideas: molarity, molarity, molarity. We're using that now just in a particular context. The context is stoichiometry. It's very similar to the mass stoichiometry that we did way back in chapter 9 and some of the other ones that we've done. It's just we're starting in a little bit of a different place. Instead of converting grams to moles, we're usually converting from molarity to moles to figure out what we've got. When we're doing our final answer, we may be using volume, maybe using mass, we may be using molarity. It just depends. So make sure you use some thought when you figure out when you've got that moles, now what do I do with it? What do I need to go with it? Neutralization reactions are just a special case. It is simply an acid-base reaction. Don't do them any differently. For some reason, your book deals with them like it's some sort of magical separate kind of problem. They're not. And then probably going along with those neutralization reactions, you probably need to review your acid names. Go back, I think they're in chapter 4, but go back and take a look at, sulfuric acid, phosphoric acid, nitric acid, carbonic acid, acetic acid. You need to remember what those are. And then the last one is limiting reactants. Limiting reactants, how do you identify those? Again, you just know the concentrations of both your reactants, and you're moving forward from there. Do not do dilution for any of these kinds of problems. That's the biggest mistake I see students make, is they look at this and go, oh, well, I can use M1V1. No. These are stoichiometry problems when you've got two different chemicals that you're dealing with. So again, if you're looking for a 4, one of the things that you could do is take a look at one of these ions that are left over, and you can do a leftover reaction. So if I did that, say that silver chromate reaction we just did, what's the number of ions of things that are left over in the problem? That's kind of challenging to do that, so that would be a really good example of a 4 problem. So there you go. I hope you enjoyed our little stoichiometry review. See you in class tomorrow.